In 2019, a defect in pacemakers by Medtronic resulted in 170,000 pacemakers being recalled. This is one of hundreds of recall incidents every year in the medical device industry, which cost companies billions due to recalls, rework, and legal and reputational damages. The global medical device market will reach 720 billion a year by 2029, and defects cost up to 10% of sales, resulting in cost of 70 billion annually. We set out to ask, how can we use AI, computer vision, and advanced algorithms to minimize defects in medical device manufacturing? Manual inspection is error-prone and inconsistent. However, traditional machine vision systems work mainly with fixed perspective 2D images without being able to locate where defects happen and collect statistical data about this location. They lost the potential to capture value from its data. MedInspect is an innovative and suite of product leveraging computer vision and multi-sensor technology to tackle the costly problem of medical device defects. Our approach creates compound value to the customer, remaining flexible for easy adoption.
Designed with modularity in mind, the product registration module allows customers to easily create a 3D point cloud of the sample product by taking a series of images with a stereoscopic camera. Only needed once, this step creates the ideal sample with both 3D form and texture information. The anomaly detection module identifies location of where defects happen and flags them with severity and confidence levels. This allows for automation of decision making such as recheck, rework, or if further inspection is required. With this, operators can free up their time to focus where their expertise matters. The defects analysis module studies the statistical data and finds patterns of where and how defects happen. This helps engineers with root cause analysis and identify improvement areas such as product redesign or any issue on the line. MedInspect consists of multiple edge sensors, on-premise software, as well as a cloud backend for more advanced analytics. This multi-sensor and modular design approach enables future connection with machinery on-site, customers' ERP systems, and even additive manufacturing solutions. It allows us to participate in all stages of the production process, and the earlier our participation, the more defects cost savings for customers. For example, unlike other solutions that only reject products at the end, we can help analyze defects during the prototyping phase or perform in situ correction for additive manufacturing. We can also perform SOPs verification for crucial environments such as the clean room. Being adaptive to manufacturing processes means that we can scale to adjacent industries with similar setup such as aerospace or chips manufacturing.
I'd like to talk about what we did this weekend in our quest to localize defects in 3D space on an object. Like we said earlier, this will allow for more accurate identification of manufacturing defects, potentially saving lives. The first step was the generation and pre-processing of the data images. We gathered both RGB and depth images of a test product using the Luxonis Oak D light. From there, we removed the background from all the images using OpenVINO and a saliency model, and exported the information to an external program for the point cloud model generation.
We'll go to market in a hybrid model. Customers purchase the sensors and hardware and pay a fee per device inspected. The fee will be priced by device complexity, targeting an average price of 1% of the device sale price. Our first focus is mid-tier companies. This will lower risk, target smaller customers who are typically more flexible, and would have a shorter sales cycle. According to our modeling, this results in $40 million yearly revenue per customer, even conservatively assuming only 10% of that would be captured. That means a sum of $16 million in 2 years. Upsells and cross-sells can include warranty services, custom development, and integrating additional sensors and sensor types. We can create a prototype for pilots with a team of 5 engineers, 2 of which are CV experts, within 6 months. Following that, scaling would require additional resources, such as data engineers and DevOps teams for the cloud components. We estimate the cost of computer resources per device scanned as minimal. Engineering costs would be approximately $500,000 a year, and overheads an additional $500,000, resulting in $1 million yearly burn rate. We would require $2 million in preliminary funding to meet the goal of developing a prototype and securing the first customer. From barely knowing anything about medical device manufacturing, we learned a lot about their problems and built a promising business case with awesome technology. From having nothing and experimenting with Luxonis and OpenVINO, we implemented 3D reconstruction and anomaly detection. Being 5 widely different individuals, we learned to coordinate, make compromises, and create synergies toward a focus goal. Thank you for your time.